There's a lie we tell ourselves about space, that it's infinite freedom, that you can go anywhere. But almost every machine we've ever sent into the darkness travels in exactly one direction. We are prisoners on a flat plane, hurtling through the void at unimaginable speed, unable to break free. And here is a question: if you could break any law of physics for a day, which would it be? And what would you do? Comment down below. I will pin the most creative answer. Now let's begin. You're hurtling through space at nearly 67,000 miles per hour. That's our planet's orbital velocity around the Sun. Every spacecraft we launch inherits that speed. And more importantly, it inherits our direction. We're moving sideways along a thin, flat disk. This disk has a name. Astronomers call it the ecliptic plane. It's the invisible table on which the solar system rests. The Sun sits near the center. Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune, all of them orbit in nearly the same flat layer. The entire architecture of our planetary family lies within a few degrees of this plane. It's not perfectly flat like a sheet of paper, but it's close. If you shrunk the solar system down to the size of a dinner plate, the planets would all be moving around within the thickness of that plate. Why? The answer goes back 4.5 billion years, to a time before there was an Earth, before there were planets at all. There was only a cloud, a massive rotating cloud of gas and dust drifting through the Milky Way. Something disturbed it, maybe the shockwave from a nearby supernova, and it began to collapse under its own gravity. As it collapsed, it spun faster. You've seen this happen before. Think of a figure skater pulling in their arms during a spin. The same principle, conservation of angular momentum, shaped our solar system. The cloud flattened into a disk, and within that disk, clumps of matter began to stick together. Those clumps became planets, the center became the Sun, and the whole system kept that original rotation, that original flatness. This is called a protoplanetary disk, and it's how most star systems form. Observations from telescopes like the Atacama Large Millimeter Array have revealed hundreds of these disks around young stars across the galaxy. They look like glowing vinyl records spinning in the dark. Our solar system was once one of them, so the ecliptic plane isn't arbitrary. It's the fossil of our birth, the scar left by the collapse of that ancient cloud, and everything in the solar system still remembers it. The planets orbit within it. The asteroid belt between Mars and Jupiter, flat. The Kuiper belt beyond Neptune, where Pluto and thousands of icy bodies drift, also flat, hugging that same plane. Even the debris, the dust, the tiny rocks, they all stay close to the ecliptic. When you look at a map of the solar system from the side, it looks like a pancake. From above, it looks like a spiral, but from the side you see the truth. We live in a two-dimensional universe, cosmically speaking, and that has consequences, because if you want to go somewhere in space, you don't start from zero, you start from 67,000 miles per hour, moving sideways. If you want to go to Mars, you're in luck. Mars is on the table with you. If you want to go to Jupiter, same thing. You're already moving in roughly the right direction. You just need to speed up or slow down, adjust your trajectory a little, and coast. But what if you want to go up? What if you want to leave the ecliptic plane and head toward the north or south pole of the solar system? What if you want to rise above the disk, to see the solar system from a bird's eye view, to explore the vast empty regions above and below the planetary orbits? That's where the problem starts, because going up, truly up, means cancelling out that 67,000 miles per hour of sideways motion. It means fighting the fundamental momentum of your birthplace. And in space, changing direction is expensive, devastatingly expensive. Spacecraft move by burning fuel. When you fire a rocket engine, you're throwing mass out the back, and Newton's third law pushes you forward. The change in velocity you achieve is called delta V, and it's the currency of space travel. Every mission has a delta V budget, a finite amount of speed you can change before you run out of fuel. To get from Earth to Mars on a typical Hohmann transfer orbit, you need about 6 kilometers per second of delta V. That's manageable. Difficult but doable. We've done it dozens of times. To get to Jupiter, maybe 9 or 10 kilometers per second, depending on the trajectory. Challenging, but we've sent probes there too. But to go straight up, to climb out of the ecliptic plane and into a polar orbit around the Sun, you'd need around 30 kilometers per second of delta V. That's the speed Earth is already moving. You'd have to stop relative to the Sun and then accelerate perpendicular to the plane. No rocket we've ever built can do that. Not even close. The energy required is simply beyond our reach. This is why almost every spacecraft we've ever launched has stayed on the table. Voyager 1, Voyager 2, Pioneer 10, Pioneer 11, New Horizons, Cassini, Galileo, all of them explored the solar system by hopping from one planet to another, moving along the ecliptic like pieces on a chessboard. They ventured outward, some of them escaping the Sun's gravity entirely, but they stayed in the plane. They had to. Even Voyager 1, the most distant human-made object, traveling through interstellar space at nearly 38,000 miles per hour, is only about 35 degrees above the ecliptic. It's tilted, but it's not truly vertical. It's still bound by the momentum it inherited from Earth. There was, however, one exception. One mission that managed to escape, one spacecraft that broke free from the flat prison of the ecliptic and climbed toward the poles of the Sun. Its name was Ulysses, and the story of how it got there is one of the most elegant pieces of orbital mechanics ever conceived. In October of 1990, the Space Shuttle Discovery lifted off from Kennedy Space Center, carrying a spacecraft unlike any before it. Ulysses was a joint mission between NASA and the European Space Agency, and its goal was simple: orbit the Sun's poles. Nobody had ever done this. Every observation of the Sun, every measurement of its magnetic field, every study of the solar wind, all of it came from our vantage point along the ecliptic. We were studying the Sun by looking at its equator, essentially. It was like trying to understand Earth by only observing the tropics. To truly comprehend our star, we needed to see its poles. But the engineers faced an impossible problem. They couldn't send Ulysses straight up. There was no rocket powerful enough. Even the most optimistic calculations showed they'd need far more energy than any launch vehicle could provide. So they devised a different plan, a brilliant, almost counterintuitive plan. They would send Ulysses outward, away from the Sun, toward Jupiter, and they would use Jupiter itself to throw the spacecraft upward. This technique is called a gravity assist, and it's one of the most beautiful tricks in spaceflight. Here's how it works. When a spacecraft approaches a planet, it falls toward that planet, accelerating as it gets closer. Gravity pulls it in. Then, as the spacecraft swings around the planet and begins to leave, it climbs back out of the gravity well, slowing down. If you only consider the spacecraft and the planet, the spacecraft leaves with the same speed it arrived with. Energy is conserved. But here's the magic: the planet itself is moving, orbiting the Sun at tremendous speed. And when the spacecraft swings past, it can steal some of that orbital momentum. Think of it like a slingshot or like a tennis ball bouncing off a moving train. The ball doesn't just bounce back at the same speed. It picks up extra velocity from the motion of the train. The spacecraft does the same thing with the planet. Jupiter was perfect for this. It's massive, 318 times the mass of Earth, and it's moving fast, orbiting the Sun at about 8 miles per second. When Ulysses arrived at Jupiter in February of 1992, it didn't just speed up or slow down. It changed direction, dramatically. The spacecraft approached Jupiter from below, passing just 227,000 miles above the cloud tops, closer than any of Jupiter's major moons. The encounter lasted only a few hours, but in that brief window, Jupiter's gravity bent Ulysses's trajectory by more than 80 degrees. The spacecraft entered moving roughly parallel to the ecliptic. It left climbing almost perpendicular to it. Ulysses was no longer traveling sideways. For the first time in the history of spaceflight, a human-made object was rising above the solar system's disk. It was going up. Over the next several years, Ulysses climbed higher and higher, eventually reaching an orbital inclination of 80 degrees. That means its orbit carried it over the Sun's south pole, then across the ecliptic near Earth's orbit, then over the Sun's north pole and back down again. It was tracing a giant loop perpendicular to the plane where all the planets live. The mission lasted 18 years, far longer than anyone expected. Ulysses completed 3 full orbits around the Sun, passing over both poles multiple times, and what it discovered changed our understanding of the Sun. The solar wind, the stream of charged particles flowing outward from the Sun, wasn't the same at the poles as it was at the equator. The magnetic field was weaker than predicted. The structure of the heliosphere, the bubble of space dominated by the Sun's influence, was more complex than anyone realized. But perhaps the most profound thing about Ulysses wasn't what it discovered, it was what the mission represented. Proof that we could escape the ecliptic, proof that the ceiling wasn't absolute. We could go up, but only if we cheated, only if we borrowed energy from a giant planet, only if we were willing to travel billions of miles out of our way just to change direction. To this day, Ulysses remains the only mission to have studied the Sun from above and below. No other spacecraft has achieved a true polar orbit around the Sun. It's simply too difficult, too expensive. And so, for the most part, we remain trapped on the table. Now, you might be wondering, why does this matter? If all the planets are on the ecliptic anyway, why would we want to go up? What's up there to explore? The answer is, more than you might think. And some of it is deeply strange. If you are enjoying this, make sure to give this video a like. Your support is the biggest fuel to keep this channel going. Now, let's start with the Oort cloud. You've probably heard of it. It's the distant shell of icy bodies surrounding the solar system, the birthplace of long-period comets. But here's what most people don't realize. The Oort cloud isn't flat. It's not confined to the ecliptic like the planets and the Kuiper belt. It's spherical, a vast three-dimensional shell extending perhaps halfway to the nearest star, filled with trillions of frozen objects left over from the formation of the solar system. These objects are small, most of them just a few miles across, made of ice and rock. They orbit the Sun, but barely. They're so far out that the Sun's gravity is weak, and they move slowly, taking millions of years to complete a single orbit. Most of them never come anywhere near the inner solar system. They just drift in the darkness, undisturbed. But sometimes something disturbs them, a passing star perhaps, or the gravitational tug of the galaxy itself. And when that happens, one of these icy bodies can be nudged inward, falling toward the Sun on a long elliptical path. When it gets close enough to the Sun to warm up, the ice begins to vaporize, forming a glowing tail of gas and dust. We call these objects comets. And here's the key point. Comets from the Oort cloud can come from any direction. They're not limited to the ecliptic. They fall toward the Sun from above, from below, from every angle imaginable. Because the Oort cloud is spherical, not flat, in 1997, one of the brightest comets in modern history appeared in our skies. Comet Hale-Bopp. It was visible to the naked eye for 18 months, one of the longest periods of visibility ever recorded for a comet. Astronomers determined it came from the Oort cloud, and its orbit was inclined by nearly 90 degrees to the ecliptic. It was falling almost straight down through the solar system, perpendicular to the planetary plane. Hale-Bopp gave us a glimpse of the vertical dimension of the solar system, a reminder that while the planets live on a flat disk, the solar system itself extends far beyond that disk, into regions we rarely explore and barely understand. And then there's the strangest visitor of all. In October of 2017, a telescope in Hawaii detected something unprecedented, an object moving through the inner solar system on a hyperbolic trajectory. That means it wasn't orbiting the sun. It was passing through, coming from somewhere else, somewhere beyond the solar system entirely. Interstellar space. They named it Oumuamua, a Hawaiian word meaning scout or messenger. It was the first confirmed interstellar object ever detected passing through our solar system. And its trajectory, it came from above the ecliptic at an angle of about 26 degrees. It fell toward the sun, swung around, and then shot back out into the galaxy, never to return. We only had a brief window to study it, a few weeks before it became too faint to observe. And what we saw was puzzling. Oumuamua was elongated, shaped like a cigar or perhaps a pancake, tumbling end over end as it traveled. It was reddish in color, suggesting a surface altered by cosmic radiation over millions of years. And strangest of all, it exhibited a small but measurable acceleration away from the sun that couldn't be explained by gravity alone. That acceleration sparked intense debate. Some scientists proposed it was outgassing like a comet, releasing jets of gas that pushed it along, but no tail or coma was detected. Others suggested it might be a fragment of a shattered planet or even a piece of frozen hydrogen ice. A few bold voices, including the Harvard astronomer Avi Loeb, speculated it could be artificial, a light sail or probe from another civilization. That hypothesis remains controversial, and most astronomers favor natural explanations. But the truth is, we don't know. Oumuamua remains a mystery. What we do know is that it came from outside our solar system, and it traveled through the vertical dimension, the dimension we rarely explore. It reminded us that the galaxy is three-dimensional. Objects can come at us from any angle, including straight down. Since Oumuamua, we've detected more interstellar visitors. In August of 2019, an amateur astronomer named Gennady Borisov discovered a second interstellar object. Unlike Oumuamua, this one looked like a comet. It had a tail, a coma, all the hallmarks of an icy body releasing gas as it warmed. They named it 2I, Borisov, and its arrival confirmed what astronomers had suspected. Interstellar objects aren't rare. They're passing through our solar system all the time. We just weren't looking carefully enough. Borisov's orbit was inclined by about 44 degrees to the ecliptic. Once again, an object from beyond our solar system came at us from an angle not along the flat plane where we live. And in late 2025, a third interstellar object was confirmed, 3I Atlas. This one appeared to be another comet detected by the Asteroid Terrestrial Impact Last Alert System in Hawaii. Early observations from the Hubble Space Telescope in late 2025 and early 2026 successfully captured its nucleus, revealing an object roughly 1.5 miles across with significant opposition surge, suggesting a surface covered in ice or highly reflective material. Researchers studying the galactic trajectories of these interstellar visitors found something fascinating. Oumuamua likely came from a young stellar system, perhaps only a few billion years old, based on how far it had strayed from the galactic plane. Borisov, on the other hand, appeared to originate from an intermediate-age population, while the trajectory of 3I Atlas suggested it may have traveled through a significant portion of the galaxy's vertical structure before reaching us. Think about that for a moment. These objects are messengers from other star systems, and they're moving through three-dimensional space. They're not confined to any particular plane. They drift through the galaxy, and occasionally, by pure chance, they fall through our neighborhood. Most of them probably pass far above or below the ecliptic, where we'd never see them. This raises an unsettling question. What else is falling through the vertical? What objects are passing through the solar system above or below the plane where all our telescopes are pointed? We have no way of knowing. We're blind in that direction. Our surveys, our detection systems, They're optimized for objects moving along the ecliptic. That's where the planets are, where the asteroids are, where most of the action happens. But the vertical is unmonitored, dark, unknown. Some astronomers have speculated about rogue planets, worlds ejected from their home star systems and drifting through interstellar space. Computer simulations suggest there could be billions of these orphaned planets wandering the galaxy, more than there are stars. Most of them would be cold, dark, invisible except by the faint infrared glow of their residual heat. And some of them might pass through our solar system. If a rogue planet fell through from above or below, traveling perpendicular to the ecliptic, would we even notice? Probably not, unless it happened to pass very close to us. And even then, detection would depend on luck, on whether some telescope happened to be pointed in the right direction at the right time. This is the ceiling problem. Not just that we can't easily go up, but that we can't easily see up either. Our exploration, our observation, our entire understanding of the solar system is fundamentally two-dimensional. We're creatures of the ecliptic, trapped on a spinning disk, mostly unaware of the vast vertical emptiness surrounding us. Now let's zoom out, because the ecliptic isn't the only flat structure in the cosmos. The galaxy itself is a disk. The Milky Way, our home galaxy, is shaped like a spiral pancake, about 100,000 light-years across, but only a few thousand light-years thick. And just like the solar system, it formed from a rotating cloud of gas that collapsed and flattened over time. Our solar system sits within that galactic disk, about 26,000 light-years from the center, in a quiet suburban arm called the Orion Spur. We orbit the galactic center at a speed of about 500,000 miles per hour, but from our perspective, we barely seem to move. It takes us 230 million years to complete one orbit. The last time we were in this part of the galaxy, dinosaurs were just beginning to walk the Earth. And here's the crucial point. The galactic disk, like the solar system's ecliptic, creates a zone of avoidance. But this time, it's not a ceiling we can't reach. It's a horizon we can't see through. Imagine looking at the night sky. When you look up or down, perpendicular to the Milky Way's plane, you're looking out of the galactic disk into intergalactic space. Your view is relatively clear. You can see distant galaxies, clusters of galaxies, the deep universe. But when you look along the plane of the Milky Way, you're looking through the disk itself, through clouds of gas and dust, through billions of stars, through layers of obscuring material. Astronomers call this the zone of avoidance. It's a band across the sky, roughly following the Milky Way's visible arc, where our view of the distant universe is blocked. In optical wavelengths, the dust absorbs starlight, creating dark patches and obscuring everything behind it. In some directions, the extinction is so severe that we can't see anything beyond our own galaxy. This matters more than you might think, because we're trying to map the universe. We're trying to understand the large-scale structure of galaxies, the cosmic web of matter stretching across billions of light-years. But there's a chunk missing from our map, a blind spot. Roughly 20% of the sky is hidden behind the Milky Way's disk. What's back there? We know there are galaxies. We know there must be galaxy clusters, superclusters, vast structures of dark matter and ordinary matter. But we can't see them directly, at least not in visible light. So we have to use other techniques. Radio telescopes can penetrate the dust. Radio waves pass through the obscuring material relatively easily, allowing us to detect the emissions from hydrogen gas in distant galaxies. Surveys like the one conducted with the Meerkat telescope in South Africa have been mapping the zone of avoidance in radio wavelengths, revealing hidden galaxies that were completely invisible before. Infrared telescopes help too. Dust that blocks visible light glows in the infrared, and the longer infrared wavelengths can pass through dusty regions more effectively. The James Webb Space Telescope, launched in late 2021, has been peering through the zone of avoidance with unprecedented clarity, finding faint galaxies obscured behind the Milky Way's disk. Observations published in late 2025 revealed hundreds of previously unknown galaxies hiding in heavily obscured regions, some of them remarkably bright once you account for the foreground extinction. But even with these techniques, the zone of avoidance remains frustrating. It's a reminder that our perspective is limited. We live inside a disk, looking outward, and that disk gets in the way. Just like the ecliptic limits our view of the solar system's vertical dimension, the galactic plane limits our view of the cosmic landscape. And there's a deeper connection here. Both zones of avoidance, the one in the solar system and the one in the galaxy, exist for the same reason: rotation. When a cloud of gas collapses under gravity, it spins, and when it spins, it flattens. This is a universal process, playing out at every scale. Galaxies, solar systems, even accretion disks around black holes, they all form the same basic shape: a disk. Disks are fundamental to the universe. They're how structure forms, how matter organizes itself, but they also create barriers, physical barriers like the ecliptic's momentum trap, observational barriers like the galactic plane's dust clouds, and conceptual barriers because we tend to think in terms of the plane we inhabit. We think sideways, we explore sideways, we observe sideways. Going up, truly embracing the vertical dimension, requires effort. It requires breaking free from the disk, either physically or perceptually, and we've only just begun to do that. Ulysses showed us it's possible to leave the ecliptic, but only by using Jupiter as a cosmic lever. Oumuamua reminded us that the galaxy is three-dimensional, that objects move through space in all directions, not just along the planes we're familiar with. The zone of avoidance surveys are revealing the hidden universe behind the Milky Way's disk, filling in the blind spots on our cosmic map, but we're still limited, still bound, in many ways, to the disks we were born into. And perhaps that's okay. Perhaps the disk is where the interesting things happen, where matter accumulates, where planets form, where life emerges. The vertical might be mostly empty, a void to be crossed, but not explored. Or perhaps we're missing something. Perhaps there are phenomena, structures, objects waiting in the vertical dimensions that we haven't even imagined yet, waiting for us to look up, waiting for us to escape the table. Let's return to the solar system for a moment, because there's more to this story. We've talked about the ecliptic, the flat plane where the planets orbit. But there are objects in the solar system that don't follow the rules. Objects with bizarre, highly tilted orbits that take them far above and below the disk. And these objects might hold clues to the solar system's violent past. One of the strangest is a dwarf planet called Sedna. Discovered in 2003 by a team led by astronomer Mike Brown, Sedna orbits the Sun on one of the most extreme paths ever observed. Its orbit is enormously elongated, taking it from about 76 astronomical units at its closest point, roughly twice the distance of Pluto, out to nearly 1,000 astronomical units at its farthest. 1 astronomical unit, remember, is the distance from Earth to the Sun, about 93 million miles. Sedna takes approximately 11,000 years to complete a single orbit. That means the last time it was where it is now, humans were just inventing agriculture, and its orbit is tilted, inclined by about 12 degrees to the ecliptic, which might not sound like much, but for an object so distant, it's significant. At its highest point above the ecliptic plane, Sedna is more than 200 astronomical units vertically displaced from where the planets orbit. But Sedna isn't alone. Astronomers have discovered a handful of similar objects, sometimes called sednoids or inner Oort cloud objects. They all share certain characteristics: extremely elliptical orbits, large semi-major axes, and most importantly, perihelia, their closest approaches to the Sun, that are far beyond Neptune. These objects never come close enough to Neptune to be influenced by its gravity. So how did they get out there? This is one of the great mysteries of planetary science. Something must have flung these objects into their current orbits. But what? One hypothesis involves stellar encounters. Early in the solar system's history, when the Sun was still part of the birth cluster of stars where it formed, a passing star might have gravitationally perturbed the orbits of distant objects, scattering them into tilted, elongated paths. Another idea involves a hypothetical ninth planet, sometimes called Planet 9 or Planet X, lurking in the outer solar system. If such a planet exists, several times the mass of Earth, and orbiting far beyond Neptune, its gravity could shepherd these distant objects into their strange orbits. Searches for Planet 9 have been ongoing for years, but so far it remains elusive. Recent studies published in 2026, using data from multiple surveys, suggest that if Planet 9 exists, it would need to have an orbit significantly inclined to the ecliptic itself, perhaps as much as 15 to 20 degrees, to explain the clustering of orbits observed among distant solar system bodies. Regardless of the cause, objects like Sedna represent the solar system's vertical frontier. They're explorers of the out-of-ecliptic regions, natural probes venturing into the emptiness above and below the planetary disk. And they're reminders that the solar system's history is more complex, more chaotic than the orderly arrangement of planets we see today might suggest. Speaking of chaos, let's talk about asteroids. Most people think of the asteroid belt as a ring of rocks between Mars and Jupiter, neatly confined to the ecliptic plane. And for the most part, that's true. The majority of asteroids orbit within a few degrees of the ecliptic, but not all of them. There are asteroids with highly inclined orbits, tilted by 30, 40, even 50 degrees or more. Some of these are likely fragments from collisions, knocked into unusual orbits by violent impacts. Others might be captured objects, originally from somewhere else, perhaps even interstellar space, pulled into orbit around the Sun by gravitational interactions with planets. And then there are the comets. We've already mentioned that long-period comets from the Oort cloud can come from any direction. But even short-period comets, those that orbit the Sun in less than 200 years, can have significant inclinations. Halley's Comet, perhaps the most famous comet of all, has an orbit inclined by about 162 degrees to the ecliptic. That's more than 90 degrees, which means it's actually orbiting the Sun backward, in the opposite direction from the planets. It's a retrograde orbit. When Halley's Comet swings through the inner solar system, it's not traveling along the ecliptic like most objects. It's cutting through the plane at a steep angle, diving down from above, passing near the Sun, and then climbing back up and away. This retrograde motion is thought to be evidence of Halley's origin in the Oort cloud, where gravitational perturbations can randomize orbital directions. Every 75 to 76 years, Halley's Comet makes its appearance, visible from Earth, a reminder that the solar system has a vertical dimension, that objects can move through space in ways that defy our earthbound intuition. The last time it visited was in 1986. The next appearance will be in 2061. If you're reading this now, you might live to see it. But here's a thought experiment. Imagine you're an astronaut on a mission to intercept Halley's Comet. You can't just launch from Earth and coast to the rendezvous. You'd need to match Halley's orbit, which means matching its inclination. That requires a massive amount of delta V, because you'd have to tilt your trajectory by more than 90 degrees relative to the ecliptic. In fact, when the European Space Agency sent the Giotto probe to study Halley's Comet in 1986, they didn't try to match its orbit. Giotto flew past at a relative speed of about 150,000 miles per hour, taking measurements during a brief high-speed encounter. Matching the comet's velocity would have been prohibitively expensive in terms of fuel, so instead they accepted a collision course trajectory, a flyby that lasted only minutes but yielded invaluable data. This is the reality of exploring the vertical dimension. It's not just difficult, it's often impractical. We can observe these tilted, out of ecliptic objects from a distance, but actually visiting them, sending spacecraft to study them up close, requires energy and resources we rarely have. So most of our missions stick to the ecliptic, where the targets are easier to reach. But what if we could change that? What if future spacecraft had more powerful propulsion systems, engines that could provide the delta V needed to break free from the ecliptic without relying on gravity assists? Technologies like ion drives, nuclear electric propulsion, or even fusion rockets could potentially make vertical exploration more feasible. Ion drives, for instance, are already in use on missions like NASA's Dawn spacecraft, which studied the asteroids Vesta and Ceres. These engines produce very low thrust, but they can fire continuously for months or years, gradually accumulating enormous amounts of delta V. A spacecraft equipped with advanced ion propulsion could, in theory, slowly change its orbital inclination, climbing out of the ecliptic over time. Nuclear electric propulsion takes this concept further. By using a nuclear reactor to generate electricity, which then powers ion engines, a spacecraft could achieve even greater delta V over long durations. NASA and other space agencies have been studying these technologies for decades, and they might become viable for deep space missions within the next few decades. And then there's the dream of fusion propulsion. If we could harness controlled nuclear fusion, the same process that powers the sun, we could build engines capable of accelerating spacecraft to a significant fraction of the speed of light. With that kind of power, leaving the ecliptic would be trivial. You could go anywhere in the solar system, in any direction, quickly and efficiently. But fusion rockets remain in the realm of science fiction, at least for now. The challenge of achieving sustained, controlled fusion is immense, and despite decades of research, we're still working on it. Experimental reactors like the ATA project in France are making progress, but we're likely still decades away from practical fusion propulsion for spacecraft, so for the foreseeable future, we're stuck with the methods we have. Chemical rockets for getting into space, gravity assists for changing direction, ion drives for missions that can afford to take their time, and a lot of careful planning because every mission has to work within a limited delta V budget. This brings us to an interesting philosophical point. The ecliptic isn't just a physical constraint, it's a mental one. We've spent the entire history of spaceflight thinking in terms of the ecliptic plane. Our maps of the solar system are drawn from above, showing the planets arrayed around the sun like beads on a string. Our mission planners plot trajectories along the plane, hopping from one planet to another. Our telescopes scan the sky along the zodiac, the band where the planets appear to move. We've optimized everything for sideways travel, and in doing so, we've created a kind of cognitive bias. We think of space as flat, even though we know it isn't. We imagine the solar system as a disk, forgetting about the vast emptiness above and below, but every once in a while, something reminds us. A comet falls from the Oort cloud, cutting through the plane at a steep angle. An interstellar object tumbles through from above, briefly visible before disappearing back into the cosmic dark. A distant dwarf planet like Sedna traces its lonely, tilted orbit, venturing far from the ecliptic plane into regions we've barely explored. These objects are messengers. They're telling us that the solar system is bigger, stranger, more three-dimensional than we usually think. They're inviting us to look up, to expand our perspective, to escape the mental groove we've been traveling in since the beginning. And maybe, just maybe, the future of space exploration lies in that direction. Not outward, not farther along the ecliptic, but up, above the plane, into the vertical unknown. There's another dimension to this ceiling problem that we haven't fully explored yet. It's not just about spacecraft and their limitations, it's about perception, about the way we experience space from our vantage point on Earth. Stand outside on a clear night and look up at the stars. What you're seeing is a dome, a celestial sphere arching overhead. Ancient astronomers believed this sphere was real, a crystalline shell studded with fixed stars rotating around the Earth. We know better now. We know the stars aren't attached to anything, that they're scattered through three-dimensional space at vastly different distances. But our perception hasn't changed. We still see them as if they're painted on the inside of a bowl. This is the tyranny of perspective. Our eyes evolved to navigate a two-dimensional surface, the ground beneath our feet. We're good at judging distances to objects at roughly our own altitude, but terrible at estimating distances to things in the sky. That bird flying overhead, is it 20 feet up or 200? Hard to say. And when it comes to stars, forget it. Without sophisticated instruments, we have no way of knowing whether a bright star is close and dim or distant and luminous. For thousands of years, this limitation shaped our understanding of the cosmos. The constellations, those patterns we see in the night sky, are completely arbitrary. They're accidents of perspective. The stars that make up Orion's belt, for example, aren't actually near each other. Alnitak, the easternmost star, is about 800 light-years away. Alnilam, in the middle, is about 1,300 light-years away, and Mintaka, to the west, is roughly 900 light-years away. They just happen to lie along nearly the same line of sight from Earth, creating the illusion of a pattern. If you could travel to another star system and look back, the constellations would be completely different. The familiar shapes would dissolve, new patterns would emerge, the sky would be unrecognizable. This realization that the stars are not on a sphere but scattered through three-dimensional space was one of the great conceptual leaps in the history of astronomy. It happened gradually over centuries as astronomers developed methods to measure stellar distances. The first reliable measurement came in 1838, when Friedrich Bessel used parallax to determine the distance to the star 61 Cygni. Parallax is simple in principle. Hold your finger up at arm's length and close one eye, then the other. Your finger appears to shift position against the background. The same thing happens with stars. As Earth orbits the Sun, our position in space changes, and nearby stars appear to shift slightly against the backdrop of more distant stars. By measuring that shift, you can calculate the distance, but the shifts are tiny. Even the nearest stars show a parallax of less than 1 arcsecond, which is 1/3600th of a degree. Measuring such small angles requires precision instruments and careful observation. Bessel's measurement of 61 Cygni, about 11 light-years away, was a triumph of 19th-century astronomy. Over time, astronomers measured the distances to more and more stars, building up a three-dimensional map of our stellar neighborhood. And what they found was that stars aren't randomly distributed. They're clustered, concentrated in certain regions, sparse in others, and most importantly, they're arranged in a disk. The galactic plane from Earth, we see this disk edge on. That's why the Milky Way appears as a band of light stretching across the sky. We're looking along the plane of the galaxy through the densest concentration of stars. When we look perpendicular to the Milky Way, up or down relative to the galactic plane, we're looking out of the disk into regions with fewer stars. This structure is clearest in star count maps. If you count the number of stars visible in different directions, you find far more stars along the Milky Way than perpendicular to it. The ratio is dramatic. Roughly 10 times as many stars lie within a few degrees of the galactic plane compared to directions far from it. But here's the interesting part. Our solar system isn't exactly in the midplane of the galaxy. We're slightly above it, displaced by about 65 light-years. That might not sound like much compared to the galaxy's overall size, but it means we're not seeing the galactic disk perfectly edge on. We're looking at it from a slight angle, tilted by less than 1 degree. This tiny tilt has consequences. It means the Milky Way doesn't appear as a perfectly symmetrical band around the sky. One half is slightly thicker, slightly brighter, because we're seeing it from above. The other half is slightly dimmer. The difference is subtle, detectable only through careful measurements, but it's there. And this displacement isn't static. The Sun, like all stars in the galaxy, oscillates vertically as it orbits the galactic center. We're currently moving upward, away from the galactic midplane. In about 15 million years, we'll reach the peak of our oscillation, about 230 light-years above the plane. Then we'll fall back down, crossing through the midplane, and continue to about 230 light-years below it. The full cycle takes roughly 60 to 70 million years. During these oscillations, the Earth's environment changes. When we're in the galactic plane, we're passing through regions of higher stellar density, more gas and dust, more potential for supernova explosions and other energetic events. Some scientists have speculated that these passages might correlate with mass extinction events on Earth, though the evidence for this remains controversial. But the point is, even stars experience a sealing problem of sorts. We're trapped in the galactic disk, oscillating up and down like a wave, but never truly escaping. The galaxy's gravity holds us in place, confining us to the disk structure just as the Sun's gravity confines the planets to the ecliptic. And if we zoom out further, the pattern repeats. Galaxies themselves aren't randomly scattered through the universe. They're arranged in structures, in clusters and superclusters, in filaments and walls, separated by vast voids. This is the cosmic web, the large-scale structure of the universe, and it too has a kind of geometry, a kind of up and down. The nearest major galaxy cluster to us is the Virgo cluster, about 54 million light-years away. It contains thousands of galaxies dominated by massive elliptical galaxies near its center. Our own galaxy, the Milky Way, along with the Andromeda galaxy and about 50 smaller galaxies, form the local group which is falling toward the Virgo cluster. But we're not falling straight toward it. We're falling at an angle because we're part of a larger structure called the Virgo supercluster, a flattened distribution of galaxy clusters extending across about 110 million light-years, and the Virgo supercluster itself is being pulled toward an even larger structure, a concentration of mass called the Great Attractor, located roughly 150 million light-years away in the direction of the constellation Norma, except we can't see the Great Attractor directly. It lies behind the zone of avoidance, hidden by the Milky Way's disk. We know it's there because we can measure its gravitational effect, the way it tugs on our galaxy and others in our vicinity. But we can't observe it in visible light. It's obscured by the dust and stars of our own galactic plane. This is frustrating for cosmologists. The Great Attractor appears to be a massive concentration of galaxies, perhaps tens of thousands of them, pulling everything in our region of the universe toward it. Understanding its structure and properties would tell us a lot about the large-scale distribution of matter, but we're stuck viewing it through the zone of avoidance, trying to peer through the fog. Recent observations have improved the situation. Radio and infrared surveys have identified some of the galaxies in that direction, revealing a dense cluster complex that might account for at least part of the gravitational pull. Advanced surveys conducted with updated infrared instruments between 2024 and 2026 have mapped nearly 2,000 galaxies in the Great Attractor region, many of them massive ellipticals that were completely invisible in previous optical surveys. But there's a twist. Further analysis suggests the great attractor itself is being pulled towards something even larger, a structure called the Shapley supercluster, about 650 million light-years away. And Shapley, along with many other superclusters, appears to be flowing toward an enormous basin of attraction that astronomers have named Laniakea, Hawaiian for immeasurable heaven. Laniakea is our home supercluster, a collection of about 100,000 galaxies spanning over 500 million light-years. It's not held together by gravity in the way a galaxy cluster is. It's more like a watershed, a region of space where all the galaxies are flowing in the same general direction toward a central basin. And here's where it gets strange. Laniakea itself is flat, not perfectly flat, but flattened, elongated, shaped more like a pancake than a sphere. The galaxies within it are distributed in filamentary structures, sheets and walls surrounding vast empty voids. It's the cosmic web in action, structure on the largest scales. Why is the universe structured this way? Why disks? Why planes? Why flat distributions of matter? The answer once again comes back to rotation and collapse. In the early universe, matter wasn't perfectly uniform. There were tiny density fluctuations, regions slightly denser than average. Gravity amplified these fluctuations. Denser regions pulled in more matter, becoming denser still. But as these regions collapsed, they didn't just fall straight inward. They had angular momentum, rotation inherited from the slight motions of matter in the early universe. And as they collapsed, that rotation caused them to flatten. Just like a spinning cloud of gas flattens into a disk, this process played out at every scale. Small fluctuations collapsed to form galaxies. Larger fluctuations collapsed to form galaxy clusters. The largest fluctuations became superclusters and the filaments of the cosmic web. And at each scale, rotation and angular momentum led to flattening. So the universe is full of disks, full of planes, full of structures that have a preferred orientation, a kind of up and down. And just like the ecliptic and the galactic plane, these cosmic structures create zones of avoidance, regions we can't easily see or explore. Let's bring this back down to something more tangible, more immediate, because the ceiling problem isn't just an abstract concept about galaxies and cosmic structures. It affects us right here, right now, in the most practical ways imaginable. Consider satellite orbits. Since the beginning of the space age in 1957, humanity has launched thousands of satellites into orbit around Earth. Most of them occupy specific zones, specific altitudes and inclinations chosen for particular purposes. And the distribution of these satellites reveals our bias towards certain types of orbits, certain orientations relative to Earth's equator. Low Earth orbit, or LEO, extends from about 100 miles to about 1,200 miles above Earth's surface. This is where most satellites live. The International Space Station orbits here, at an altitude of roughly 250 miles. The Hubble Space Telescope is here, at about 330 miles, and thousands of communication satellites, Earth observation satellites, and scientific instruments circle the planet in this zone. But here's the key detail. Most LEO satellites orbit at low inclinations, meaning their orbital planes are tilted only slightly relative to Earth's equator. The ISS, for example, orbits at an inclination of about 51.5 degrees. That might sound like a lot, but it means the station never travels farther north than 51.5 degrees latitude or farther south than 51.5 degrees south latitude. It never passes over the polar regions. Why? Because the ISS launches from sites at mid-latitudes, the Baikonur Cosmodrome in Kazakhstan and Cape Canaveral in Florida. When you launch a rocket into orbit, the most efficient trajectory is one that matches the latitude of your launch site. Changing your inclination after launch requires enormous amounts of fuel. just like we discussed with escaping the ecliptic. So the ISS's orbit is a compromise, tilted just enough to be accessible from both Russian and American launch sites. Most commercial satellites follow a similar logic. Communication satellites often use geostationary orbit, a special altitude of about 22,236 miles, where the orbital period exactly matches Earth's rotation. A satellite in geostationary orbit hovers over the same point on the equator, appearing stationary from the ground. This makes them perfect for television broadcasting, weather monitoring, and telecommunications. But geostationary orbit only works at 0 degrees inclination. If your orbit is tilted relative to the equator, you're not geostationary anymore. You're geosynchronous, which means your orbital period still matches Earth's rotation, but you appear to drift north and south over the course of a day, tracing a figure-8 pattern in the sky. That's less useful for most applications, so the vast majority of geostationary satellites stay right above the equator. This creates a crowded zone. There are hundreds of satellites parked in geostationary orbit, spaced every few degrees around the equator. They have to be carefully positioned to avoid interfering with each other's signals. It's like a cosmic parking lot, and we're running out of spots. Meanwhile, the polar regions are relatively neglected. There are polar orbiting satellites, of course. Weather satellites use polar orbits because they pass over every part of Earth as the planet rotates beneath them. Reconnaissance satellites use polar orbits for the same reason, but there are far fewer satellites in polar orbits compared to equatorial or mid-inclination orbits, and highly inclined orbits, those tilted by more than 90 degrees, are rare. They exist mostly for specialized applications like certain spy satellites or scientific missions, but they're expensive to reach. Launching into a highly inclined orbit requires fighting against Earth's rotation instead of using it to your advantage. Earth rotates at about 1,000 miles per hour at the equator. If you launch eastward from the equator, you get that speed for free, a boost that reduces the amount of fuel you need to reach orbital velocity. But if you launch into a polar orbit, you don't get that boost. And if you launch into a retrograde orbit, going against Earth's rotation, you're actually starting with a penalty. You have to cancel out Earth's rotation and then add the velocity you need for orbit. It's expensive. This is why most launches happen from sites as close to the equator as possible. The European Space Agency launches from French Guiana at about 5 degrees north latitude. The United States launches from Florida at 28 degrees north. Russia launches from Baikonur at 46 degrees north, which isn't ideal, but it's what they have. And recently, commercial launch providers have started using ocean platforms, essentially launching from mobile platforms positioned near the equator to maximize efficiency. But this optimization for equatorial launches reinforces the ceiling problem. We've built our entire space infrastructure around the assumption that going sideways around the equator is easier than going vertical toward the poles or beyond. And that assumption is correct given our current technology, but it limits us. It limits where we can observe from. Satellites in equatorial orbits can't see the polar regions very well. They're always looking at them from an angle, from a distance. If you want high-resolution images of Antarctica or the Arctic, you need satellites in polar orbits, and those are harder and more expensive to deploy. It limits what we can monitor. Climate scientists studying polar ice caps, oceanographers tracking sea ice extent, they all rely on data from polar orbiting satellites. But there are fewer of these satellites, and they're more expensive to maintain. So the data is sparser, the coverage is less frequent, and it limits our thinking. When we design satellite constellations, when we plan communications networks, when we imagine the infrastructure of space, we tend to think in terms of the equator, We think in terms of geostationary orbit, low Earth orbit at familiar inclinations, paths that follow the curve of Earth's rotation. But what if we thought differently? What if we embraced the vertical? There's a concept in orbital mechanics called a Molniya orbit, named after a series of Soviet communications satellites. It's a highly elliptical orbit with a high inclination, usually 63.4 degrees, that takes advantage of a quirk in orbital mechanics. At that specific inclination, the gravitational perturbations from Earth's equatorial bulge cancel out in a particular way, keeping the orbit stable over long periods. A satellite in a Molniya orbit spends most of its time at high altitudes over the northern hemisphere, moving slowly along the most distant part of its ellipse. This makes it perfect for providing communications coverage to high-latitude regions like Russia, Canada, and Scandinavia. For several hours, the satellite appears nearly stationary in the sky, allowing ground stations to track it easily. Then it swoops down, passes quickly through the southern hemisphere, and climbs back up to repeat the cycle. The Soviet Union used Molniya orbits extensively because geostationary satellites don't work well for high-latitude coverage. If you're in Moscow or Siberia, a geostationary satellite appears very low on the horizon, often blocked by buildings or terrain, but a satellite in a Molniya orbit passes almost directly overhead, providing excellent line-of-sight communication. This is an example of thinking vertically. Instead of fighting to stay above the equator, Molniya orbits embrace the tilt, use it to their advantage, and they work. Russia still uses them today, alongside more modern geostationary satellites. Another vertical innovation is the tundra orbit, similar to Molniya, but with an even higher altitude and a one-day orbital period. Satellites in tundra orbits can provide continuous coverage of high-latitude regions with just a few spacecraft, making them useful for communications, navigation, and surveillance. And then there's the idea of statites. This is more speculative, but bear with me. A statite is a hypothetical satellite that uses solar sails to hover above a planet at a non-traditional location. Normally, a satellite has to orbit. If it's not moving fast enough, it falls. But a statite uses the pressure of sunlight on a large reflective sail to counteract gravity, allowing it to remain stationary above a point on the planet without orbiting. With a statite, you could, in theory, position a satellite directly above the North Pole or the South Pole, hovering there indefinitely. It wouldn't be in orbit. It would be balanced between gravity pulling it down and the solar sail pushing it up. You could place them at any latitude, any altitude, breaking free from the constraints of orbital mechanics. Statites remain theoretical. The engineering challenges are immense. You'd need an enormous sail, kilometers across, made of incredibly thin, lightweight material. You'd need precise attitude control to keep the sail angled correctly, and you'd have no sail pressure when the satellite passes into Earth's shadow, so you'd need another way to maintain position during those periods. But the concept illustrates an important point. Our current approach to satellites and orbits is based on working within the constraints of gravity and rotation. We optimize for efficiency, choosing orbits that minimize fuel consumption. But with new technologies, with solar sails or ion drives or other advanced propulsion systems, we might be able to break those constraints. We might be able to position satellites wherever we want, regardless of orbital mechanics. Imagine a future where satellites aren't confined to specific orbital shells, where they can move freely, adjusting their position and altitude as needed, where coverage isn't limited by inclination and orbital period, where the vertical dimension is just as accessible as the horizontal. That future might not be as far off as you think. The Starlink constellation, SpaceX's network of thousands of small satellites providing global internet coverage, represents a step in that direction. Starlink satellites use ion thrusters to adjust their orbits, avoiding collisions and maintaining their positions within the constellation. They're launched into a variety of orbital planes, including high-inclination shells that provide coverage to polar regions. As of early 2026, SpaceX has deployed over 6,000 Starlink satellites, with plans to expand to tens of thousands. The constellation includes satellites in polar orbits, providing internet access to research stations in Antarctica and remote communities in the Arctic. It's not perfect, but it's a move toward more comprehensive, three-dimensional coverage. Other companies and countries are developing similar constellations. OneWeb, Amazon's Project Kuiper, China's Guoang constellation, all aiming to blanket the Earth with satellites, providing communications and internet access to every corner of the planet. And many of these constellations include high-inclination orbits, recognizing that equatorial coverage alone isn't enough. But these constellations also create new problems. Thousands of satellites in low Earth orbit mean thousands of potential collisions. Space debris is already a serious concern, and adding more satellites makes it worse. Each collision creates more debris, which can trigger more collisions in a cascade effect known as Kessler syndrome. And then there's the issue of light pollution. Satellites in low Earth orbit reflect sunlight, appearing as bright streaks in the night sky. For astronomers, especially those using large ground-based telescopes, these streaks ruin observations, contaminating images and interfering with scientific research. SpaceX has tried to mitigate this by adding visors to their satellites, reducing reflectivity, but the problem persists. So we've created a new ceiling, a different kind of barrier. Not one imposed by physics or orbital mechanics, but one we've built ourselves. A shell of satellites and debris encircling the planet, a layer we have to navigate through carefully, a zone that's becoming increasingly crowded and contested. This is the Kessler problem, named after NASA scientist Donald Kessler, who first described it in 1978. The idea is simple but terrifying. If the density of objects in orbit becomes too high, collisions become inevitable. Each collision creates fragments, hundreds or thousands of pieces of debris traveling at orbital velocity. These fragments can then collide with other satellites, creating more debris, which creates more collisions in a runaway cascade. Eventually, if left unchecked, this cascade could render certain orbital zones unusable. Low Earth orbit could become so filled with debris that launching new satellites becomes impossible. Every spacecraft would face an unacceptable risk of collision. We'd be trapped on our own planet, surrounded by a shell of our own garbage, unable to reach space. Is this happening? Are we approaching a Kessler cascade? The answer is complicated. We're not there yet, but we're moving in that direction. The number of tracked objects in orbit has been growing steadily. As of 2026, there are approximately 36,000 objects larger than 10 centimeters being tracked by the US Space Surveillance Network. These include active satellites, dead satellites, spent rocket stages, and fragments from collisions and explosions. But that's just what we can track. There are an estimated 130 million objects larger than 1 millimeter in orbit, too small to track individually but large enough to cause damage. A fleck of paint traveling at 17,000 miles per hour hits with the force of a bullet. It can punch through metal, shatter solar panels, damage sensitive instruments. Several major collisions have already occurred. In 2009, an active American communications satellite, Iridium-33, collided with a defunct Russian military satellite, Cosmos 2251. The collision occurred over Siberia at a relative velocity of about 26,000 miles per hour. Both satellites were completely destroyed, creating more than 2,000 trackable pieces of debris and countless smaller fragments. That debris is still up there, spreading out along the orbital paths of the original satellites. creating a hazard for other spacecraft. Some of it will eventually fall back to Earth and burn up in the atmosphere, but that process takes decades at those altitudes. In the meantime, it's a persistent threat. Then in 2007, China conducted an anti-satellite missile test, deliberately destroying one of their own defunct weather satellites, Fengyun 1C, at an altitude of about 530 miles. The test was successful in demonstrating China's capability to destroy satellites, but it created the largest debris cloud in history. More than 3,000 trackable fragments and an estimated 150,000 smaller pieces. This debris will remain in orbit for centuries. It's spread across a range of altitudes, intersecting the orbital paths of many active satellites, including the International Space Station. Astronauts on the ISS have had to shelter in their Soyuz escape capsules multiple times because of close approaches by debris from this single test. These events demonstrated the fragility of the orbital environment. One reckless action, one collision, can have consequences that last for generations. And as we continue to launch more satellites, the risk increases. So what can we do about it? How do we prevent the Kessler cascade? One approach is active debris removal. Build spacecraft specifically designed to capture and deorbit defunct satellites and large debris. Several concepts have been proposed and tested. The Remove Debris mission, launched in 2018, demonstrated technologies like nets, harpoons, and drag sails for capturing debris. The ClearSpace 1 mission, planned by the European Space Agency for launch in 2026, is designed to rendezvous with a defunct payload adapter and guide it into a controlled re-entry. In late 2025 and early 2026, Japan's ADRAS-J mission successfully demonstrated close proximity operations with a large piece of orbital debris, providing detailed imagery and confirming the feasibility of future removal operations. These missions represent critical first steps, proof that we can develop the technology to clean up our orbital environment. But active debris removal is expensive. Each mission can cost tens or hundreds of millions of dollars, and there are thousands of large objects that pose a threat. Scaling up to address the entire problem would require a massive investment, sustained over decades, and who pays for it? The companies that launched the satellites, the countries that own them, international cooperation. Another approach is designing satellites with end-of-life disposal in mind. Modern satellites are increasingly equipped with propulsion systems that allow them to deorbit themselves when their mission is complete. Instead of becoming debris, they use their remaining fuel to lower their orbit until atmospheric drag pulls them down to burn up. This is now required for new satellites in certain orbits. Regulations from the Federal Communications Commission and other agencies mandate that satellites in low Earth orbit must deorbit within 25 years of mission completion. But compliance is voluntary for many older satellites, and enforcement is difficult. There's also the concept of just-in-time collision avoidance, where satellites actively maneuver to dodge debris. This requires accurate tracking, rapid computation of collision probabilities, and automated decision-making. Starlink satellites, for example, use onboard autonomous systems to detect potential collisions and execute evasive maneuvers without human intervention. But this creates a coordination problem. If multiple satellites are trying to avoid the same piece of debris, they need to communicate with each other to ensure they don't maneuver into each other's paths. As the number of satellites increases, the complexity of this coordination grows exponentially. Some researchers have proposed traffic management systems for space, analogous to air traffic control, a centralized or distributed system that tracks all satellites and debris, predicts collisions and coordinates maneuvers. But implementing such a system faces technical, political, and legal challenges. Who has the authority to direct satellites owned by different countries and companies? What happens when interests conflict? These are questions we're grappling with right now in 2026 as the orbital environment becomes more crowded, and they're questions that don't have easy answers. But let's zoom out again, because the debris problem is just one manifestation of a larger issue, our relationship with the vertical dimension. We treat space as a place to pass through, not a place to inhabit. We send satellites up, use them for a while, and then abandon them. We treat orbital zones as disposable, as infinite, even though they're anything but. This is a failure of imagination and a failure of responsibility. If we want a future in space, if we want to move beyond Earth and explore the solar system and beyond, we need to change our approach. We need to start thinking of space as an environment that requires stewardship, not exploitation. And that means thinking vertically, not just in terms of how to get from one orbital plane to another, but in terms of how we structure our presence in space, how we organize our satellites, our stations, our infrastructure across the three-dimensional volume available to us. Right now, our satellites are concentrated in a few specific zones: low Earth orbit, geostationary orbit, a handful of other special orbits like Molniya and Polar. These zones are like highways, well-traveled routes that everyone uses because they're efficient and well understood. But highways get congested, and when they do, we need alternatives. What if we spread out more? What if we used a wider range of altitudes and inclinations, distributing our satellites across more of the available space? This would reduce the density in any one zone, lowering collision risks, but it would also require more energy, more sophisticated propulsion systems, more complex operations. Or what if we moved some functions out of Earth orbit entirely? Instead of placing communication satellites in geostationary orbit, what if we positioned them at Lagrange points, those special locations where the gravitational forces of Earth and the Sun balance out? There are 5 Lagrange points in the Earth-Sun system. L1 is between Earth and the Sun, about 930,000 miles from Earth. L2 is on the opposite side of Earth from the Sun, about the same distance. L3 is on the far side of the Sun. L4 and L5 are 60 degrees ahead of and behind Earth in its orbit, forming equilateral triangles with Earth and the Sun. Satellites at these points experience a kind of gravitational equilibrium. They still need occasional adjustments to stay in place, but much less than satellites in other orbits, and they offer unique vantage points. L1 is perfect for solar observatories, watching the Sun without Earth getting in the way. L2 is ideal for space telescopes, looking out at the universe with Earth, the Moon, and the Sun all behind them, providing a stable thermal environment. The James Webb Space Telescope operates at L2. So does the European Space Agency's Gaia spacecraft, which is mapping the positions and motions of over 1 billion stars. These missions demonstrate the value of thinking beyond traditional Earth orbits, using the three-dimensional structure of the solar system to our advantage. But L2 is getting crowded too. As of 2026, there are multiple missions operating there, and more are planned. Eventually, we might face coordination challenges similar to those in geostationary orbit. We're running out of prime real estate. Even 1 million miles from Earth, this might sound absurd. Space is enormous. How can we possibly be running out of room? But it's not about the total volume. It's about the specific valuable locations, the orbits and positions that offer the best combination of access, stability, and utility. Those locations are finite, and we're filling them up. So perhaps the real ceiling isn't physical. It's not about delta V or propulsion technology. It's about our willingness to venture into less convenient, less familiar regions of space, to accept higher costs, more complex operations, in exchange for greater freedom and sustainability. This is a choice we face not just with satellites, but with human spaceflight too. The International Space Station orbits at 51.5 degrees inclination, limiting where astronauts can observe and work. Future space stations might choose different inclinations or even operate at multiple inclinations, requiring crews to transfer between them. China's Tiangong space station, completed in 2022, orbits at 42 degrees inclination, optimized for launches from Chinese spaceports. India has announced plans for a space station at a higher inclination, providing better coverage of Indian territory. We're seeing a diversification, a recognition that one-size-fits-all doesn't work for orbital infrastructure. And looking further ahead, proposals for lunar infrastructure include stations at the Moon's Lagrange points, particularly L2, which offers continuous line-of-sight communication with the far side of the Moon. NASA's Gateway Station, planned as part of the Artemis program, will operate in a near-rectilinear halo orbit around the Moon, a complex trajectory that passes close to the lunar surface and then swings out to high altitude. These orbits are not intuitive. They're not simple circles or ellipses. They're three-dimensional curves shaped by the combined gravitational influences of Earth and the Moon, requiring precise navigation and station keeping. But they offer capabilities that traditional lunar orbits don't: the ability to support missions to any part of the Moon, to serve as a staging point for deeper space exploration, to operate in a stable, efficient manner. This is vertical thinking in action. Not accepting the limitations of traditional orbits, but exploring the full three-dimensional space of possibilities. Let's try to understand what the ceiling problem really means, and what it tells us about our place in the universe. We started with the ecliptic, that flat plane where the planets orbit the Sun. We talked about how difficult it is to escape that plane, how much energy it requires, how our entire solar system is structured around this fundamental geometry. We explored the galactic plane, the Milky Way's disk, and saw the same pattern repeat at a larger scale. We looked at the cosmic web, at galaxy clusters and superclusters, and found flatness everywhere. And then we brought it back home, to Earth orbit, to the satellites and debris circling our planet, to the infrastructure we're building in space. And we found the same constraints, the same tendency toward preferred planes, the same difficulty in moving vertically. What does this pattern tell us? It tells us that the universe has structure, that gravity and rotation, the two fundamental forces shaping celestial mechanics, naturally create planes and disks. That angular momentum is conserved, that energy must be expended to change inclination, that the path of least resistance is always to stay within the plane you started in. But it also tells us something about ourselves, about human nature and our relationship with exploration. We are creatures of the horizontal. We evolved on a surface, moving across terrain, navigating in two dimensions. Our minds are built for maps, for networks of roads and rivers, for understanding space as a flat expanse with landmarks and boundaries. Even when we ventured into the oceans, we stayed on the surface. Submarines came later, and even today, most ocean travel happens at the interface between water and air. The vertical dimension is alien to us. It's harder to visualize, harder to navigate, harder to control. Going up requires constant effort, constant expenditure of energy. Gravity is always pulling us down. And in space, where there is no up or down in the conventional sense, we create our own planes, our own reference frames, and then we struggle to leave them. This is the ceiling problem in its deepest sense. Not a physical barrier, but a conceptual one. A limitation born from the way we think, the way we navigate, the way we understand the universe. But here's the thing, we can overcome it. We have overcome it repeatedly throughout history. When ancient astronomers believed the stars were fixed to a crystalline sphere, they were prisoners of their perception. They couldn't imagine the vertical dimension of space, the vast distances between stars. But then telescopes and parallax measurements revealed the truth, and suddenly the universe became three-dimensional. The ceiling shattered. When early rocket scientists struggled to reach orbit, they faced enormous technical challenges. The energy requirements seemed insurmountable. But they persevered, developed more powerful engines, more efficient fuels, better guidance systems. And on April 12, 1961, Yuri Gagarin broke through the ceiling, becoming the first human in space. When NASA wanted to send probes to the outer solar system, they faced the tyranny of the rocket equation. They couldn't carry enough fuel to reach Jupiter, Saturn, Uranus, Neptune. The ceiling seemed absolute. But they found a way around it: gravity assists, using planetary flybys to gain velocity without fuel. The Voyager probes, launched in 1977, are now in interstellar space, still transmitting data from beyond the heliopause. They broke through another ceiling. And when we face the debris problem today, when we worry about Kessler syndrome and orbital congestion, we're confronting another ceiling. But we're also developing solutions: active debris removal, better tracking, international coordination, new regulations. We're learning to be stewards of the orbital environment, not just exploiters of it. You're exactly the kind of person I make these videos for. Make sure to subscribe to the channel so you don't miss the next deep dive. Whether we're exploring the physics of impossible orbits, the engineering of interstellar travel, or the next ceiling humanity will break through, every ceiling we encounter teaches us something. It forces us to innovate, to think differently, to question our assumptions. And when we break through, we discover new possibilities, new frontiers, new questions. So what's the next ceiling? What barrier will we face next? Maybe it's the speed of light. Right now, our fastest spacecraft, the Parker Solar Probe, travels at about 430,000 miles per hour relative to the Sun. That's incredibly fast by human standards, but it's only about 0.064% the speed of light. At that speed, it would take over 6,000 years to reach Proxima Centauri, the nearest star to our Sun. Interstellar travel, real interstellar travel, requires speeds that are a significant fraction of light speed. 10%, 20%, maybe more. We don't know how to achieve those speeds with current technology. Chemical rockets won't work. Nuclear propulsion might help, but even that has limits. We might need something entirely new: fusion drives, antimatter engines, laser-pushed light sails, concepts that exist on paper but haven't been demonstrated. This is a hard ceiling, maybe the hardest we've faced. The laws of physics are unforgiving. As you approach the speed of light, your mass effectively increases, requiring more and more energy to accelerate further. You can never quite reach light speed if you have mass. It's an asymptote, a limit that can be approached but never crossed. Or maybe the next ceiling is biological. Human bodies evolved for Earth's gravity, Earth's atmosphere, Earth's magnetic field protecting us from radiation. In space, our bones lose density, our muscles atrophy, our cardiovascular systems struggle. Astronauts on the ISS exercise for hours every day just to maintain their health, and even then, they experience long-term effects. Going to Mars means months in zero gravity, followed by months in Mars's weak gravity field, which is about 38% of Earth's. We don't fully understand the long-term health consequences. We don't know if humans can reproduce in space, if fetuses can develop properly in reduced gravity. These are fundamental questions that we haven't answered yet because we haven't tried. If human biology can't adapt to life beyond Earth, then our expansion into space might be limited to short-term visits, protected habitats, or eventually modification of our own biology. Genetic engineering, cybernetic enhancement, uploading consciousness into machines. Science fiction concepts, but may be necessary if we truly want to become a spacefaring species. Or maybe the next ceiling is social and political. Space exploration requires massive resources, sustained commitment, international cooperation. The Apollo program succeeded because the United States poured resources into it, driven by Cold War competition. But that level of commitment has been hard to maintain. Budgets fluctuate, priorities shift, political winds change. The International Space Station represents an achievement in cooperation, bringing together the United States, Russia, Europe, Japan, and Canada. But that cooperation is fragile, tested by geopolitical tensions. As of 2026, relations between Russia and the West remain strained following the events in Ukraine. China operates separately, building its own station, pursuing its own lunar program. Will we continue to cooperate, or will space become another arena for competition and conflict? Will we establish rules and norms for behavior in space, or will it become a free-for-all, each nation and corporation pursuing its own interests? These questions will shape the future of space exploration as much as any technology. But despite all these ceilings, despite all these challenges, I remain optimistic. Because humans are stubborn, we're curious, we push boundaries, we explore, we refuse to accept limitations as permanent. Look at what we've accomplished in less than 70 years since Gagarin's flight. We've walked on the moon. We've sent robots to every planet in the solar system. We've landed spacecraft on asteroids and comets. We've operated a telescope at the L2 point that can see galaxies forming in the early universe. We've discovered thousands of planets around other stars, and we're beginning to characterize their atmospheres, searching for signs of life. And right now, in 2026, there are multiple missions underway or planned that are pushing boundaries even further. NASA's Artemis program is working to return humans to the moon and establish a permanent presence there. SpaceX is developing Starship, a fully reusable launch vehicle designed to carry humans to Mars. China is planning crewed lunar missions. India is expanding its space program. Private companies are developing space tourism, orbital manufacturing, asteroid mining concepts. We're at an inflection point. For the first time in history, space is becoming accessible not just to governments with massive budgets, but to private companies, to smaller nations, even to individuals with sufficient resources. The cost of reaching orbit has dropped dramatically thanks to reusable rockets and increased competition. What cost tens of thousands of dollars per kilogram a decade ago now costs a tenth of that, and the trend is continuing downward. This democratization of space access changes everything. It means more missions, more experiments, more innovation. It means diverse perspectives and approaches. It means that solutions to the ceiling problem will come from unexpected places. Maybe a startup will develop a breakthrough propulsion technology. Maybe an international collaboration will demonstrate active debris removal at scale. Maybe a scientist in a country that's never had a space program will discover a new approach to radiation shielding or life support. The more people working on these problems, the more likely we are to solve them. And ultimately, that's what the ceiling problem is about. It's not about accepting limitations. It's about recognizing them, understanding them, and then finding creative ways to transcend them. The ecliptic isn't a prison, it's a starting point. Yes, it takes energy to leave it, but we have energy. We have the sun, pouring out power constantly. We're learning to harness it more efficiently, with better solar panels, with solar sails, with concepts for solar power satellites that could beam energy wherever it's needed. The galactic plane isn't a barrier. It's our neighborhood, the region we understand best. But it's not the only place we can go. We can send probes upward and downward, mapping the galaxy in 3 dimensions, understanding its structure, exploring regions we've never studied before. And Earth orbit isn't a junkyard, it's infrastructure. It's an environment we need to manage responsibly, but it's also the foundation for everything we'll do beyond Earth. Every mission to the Moon, to Mars, to the asteroids starts from Earth orbit. It's our first step, our gateway to the solar system. So yes, there are ceilings, there are planes and disks and preferred orientations created by the fundamental physics of rotation and gravity. There are challenges ahead, technical and biological and social, that we haven't fully solved, but we're not trapped. We've never been trapped. Every ceiling we've encountered, we've eventually broken through. Sometimes it takes years, sometimes decades, sometimes centuries, but we get there. And when we do, when we finally figure out how to move freely in 3 dimensions, when we build the infrastructure to travel between stars, when we establish civilizations beyond Earth, we'll look back at this moment, at the early 21st century, and we'll remember it as the time when we were still learning to fly, when we were still figuring out how to escape the plane, how to break through the ceiling, how to embrace the infinite vertical dimension that's always been there, waiting for us. The universe is 3-dimensional. We just need to learn to live in all 3 dimensions. That's the challenge. That's the opportunity. That's the future we're building. One mission, one innovation, one breakthrough at a time.